Whee! Okay, let's relax a little bit and let's get our mind, where are we doing? What are we doing in chemistry class? What I did was, we do have a quiz tomorrow, but it's going to be on the second half of the period, okay? And the quiz is about take about 20 minutes. I'll give you 30 minutes, but it'll probably take about 20 minutes for most people to take it. And let's talk about, what would you put on a quiz to see what we've been doing? How well do you know what we've been doing? So what do you think? What would be on there? We talked about this one other time. I'll do it again. Do you think I might ask about something about water? Okay, do you remember that, even though it was way back in chapter 15, remember the page about how water is polar? Could you write a little story about that? Could you tell me what the intra and the intermolecular bonding is for water? I said, well, wait a minute, I don't know about that. Why is water a polar molecule? What kind of things do water, what kind of things can it dissolve? Why would water be able to dissolve so many ionic compounds?
It's the hydrogen. Polar. It's a polar
Okay,
molecule.
right. So the water is a plus and minus nature, doesn't it? Polar molecule, and ionic compounds are plus and minus, aren't they? So you can see how it's going to dissolve, and not only dissolve ionic compounds, but break the ions apart, aren't they? What about something like alcohols? Does water dissolve? Alcohols dissolve in water? They do, because even though they're made of only carbon, hydrogen, oxygen, non-metal, they're not ionic. But part of them is an O bonded to an H. And who wins in that battle? They're supposed to share a pair of electrons, but who always wins between O and H? O always brings the negative electrons toward it. So alcohols end up being a polar molecule, and now it has a plus-minus nature, and water has a plus-minus nature. So yes, alcohols do dissolve in water, don't they? What if I go to the store and buy 70% rubbing alcohol? What's in there? Water and alcohol. And we do that. We know they mix, don't they? Even table sugar. Table sugar is made of C, H, and O. There's a whole bunch of covalent bonds, right? But a whole bunch of those are OH, OH, OH. So many parts of a sugar molecule are polar. And so even sugar dissolves very well in water. What kind of things do not dissolve very well in water? What is it? What are they called? What big group of chemicals would you call, like paraffin and oil and gasoline? Hydrocarbons, aren't they? And when you only have carbon and hydrogen, the bonding is very equal, the sharing of electrons. So those are non-polar, and that's why they don't mix with water. All right, some other things. Remember this chart? I'll give you this chart. But here's a question I might ask. I have some sodium nitrate. I'm going to put it in some water and stir it. Will I still see the sodium nitrate?
No.
How do you know that? That's pretty fast.
Because
And I'll give you the chart, but you already know how to do the faster method. You say, I already know that all nitrates are what? So I'm not going to see the sodium nitrate. What if I say silver chloride? You say, well, wait a minute. Oh, solid. All right, so even if I tried to stir the silver chloride up, it will not dissolve it. So some ionic compounds are soluble in water, right? And some are what? Insoluble. So, all right. That'd be pretty, what do you think? That fair question to ask that? Okay. What about, let's go back to the question before this. I put some sodium nitrate, wait a minute. I put some, sodium nitrate in water and I stir it up. I don't see it, do I? But would that solution conduct electricity? Would that solution be an electrolyte?
Yes.
Yeah, because the ions, right? Now let's go back and put some table sugar. It dissolves because it's polar. But does it break up into ions?
No.
It's not made of ions. So it would not conduct, it'd be a non-electrolyte, wouldn't it? So just because you dissolve, it doesn't mean you break up into ions. Ionic compounds are already made of ions before you put them in water, isn't it? Water just simply separates the ions and lets them float around. Are you okay with that? Yes. You okay with this, right? All right. I forgot what it was. Was it yesterday or 2 days ago? You did a good job. You caught something. I forget. Remember that? Hey, you caught. I forget what it was. All right. So here's where we're going to go. We had. This is a review. Okay. This would be on there too. You found out that we did this last chapter. Can you write a balanced chemical equation? We did that last chapter, didn't we? Are you okay on that? Okay, so what's new about this chapter? What's new about this chapter is we started adding these little things there, didn't we? And so here's a double replacement reaction. We start with two solutions. Can I see that chemical? No. Can I see this one? No. But when I put them together, is a reaction going to take place? You said, well, last chapter, I would have just written it down, double replacement, I would have done it. But with this chapter, you found out there's a little bit more to chemistry than just that. Is it going to happen? You said, well, what are the two products going to be? Ammonium nitrate and lead 2 chloride. Now, all the ammoniums are soluble and all the nitrates, so far, I don't have a driving force. It looks like it's not going to happen. But what about that lead 2 chloride? And I look it up, and I found out it's going to be a precipitate, isn't it? Isn't that right? What do you call an insoluble product? These are the two products. Soluble, insoluble. It's a precipitate. Yes? So what is a special type of double replacement in which the formation of a solid is the driving force? What do you call it? Precipitation reaction. You are correct. And again, in the book, I've never asked you to read every single page of the chapter. I have always asked you to scan the chapter. You look at pictures, you look at dark print words, and I can show you right now, if I go to that page right there, you'll see the word precipitate, precipitation reaction, soluble, insoluble. All the things we talked about are in here, okay? All right. Now, the thing you had never done before is put these little symbols after it. You never really worried about driving force. Now, here's where you had to be a little more grown up, okay? And that's why I thought this chapter is truly an honors class chapter. You have to understand what is in that beaker. What's in that beaker besides water? All right, so it's 2 ammonium ions for every... No. Here, cover up the 2. Ammonium chloride. How many ammonium chlorides do I have? Ammonium chloride? Ammonium chloride. I have 2 ammonium chlorides, don't I? How many ammonium ions would that be? 2. And how many chloride ions? And do I have to put the +1 here? Yes, it's an ion. Do I have to put AQ? Yes, it's dissolved in water. Okay, now what about here? What's in that beaker? 1 lead ion. And be careful. There is no diatomic nitrate. But my eyes see a subscript of 2. What does that mean? What's this thing made of? It's made of 1 of these ions and what? 2 nitrates. Isn't that right? That's why I put a 2 here as a coefficient, didn't I? Now what about here? What's over here? 2 ammonium ions and what? See that? And what about here? Lead 2 chloride. I don't split this up. Why not? What is it? It's a solid, isn't it? And it's my driving force. It's why the reaction takes place. If both of these products had been soluble, you put a big NR there. What's that mean? No reaction. Yeah, last chapter you would have said, yeah, there's a chemical reaction. I know how to balance an equation. This chapter you find out that might not happen. All right, you okay on that? So the complete ionic equation is the longest equation you'll ever write. And then the fun part is I get to cross out the, what's that vocabulary word? I get to cross out the what?
Spectators.
Spectator ions, right? And spectator ions on the left side of the arrow, they look identical to on the right-hand side of the arrow. Hey, that was 2 ammoniums floating around, and there's 2 ammoniums floating around. You didn't do anything. You're right. You're out. As a matter of fact, if you had balanced the equation wrong, you should be able to catch your mistake here. What if I had 2 here and only 1 here? Ooh, I better go back and check. I probably balanced it wrong, see? And what else was a spectator ion? Nitrate and nitrate. So whatever's left is the real chemistry. The net ionic equation says what really happened. 2 chloride ions did what? Combined with 1 lead ion and made lead 2 chloride. That's it. That's the only chemistry that took place. Now here's a hard question. If this happened in a beaker and I stuck a probe in there, would it be an electrolyte? Well, I'll give you a hint. These ions are not going to conduct any electricity because they're together. But would it be an electrolyte? Yeah, you know who's still in the beaker? Who's still sitting around in the beaker? Yeah, the spectator ions, is that right? They're still there, aren't they? Okay. Now, another thing I was trying to get you to do is to do a thing called a shortcut, okay? Now, yes, it's true on the quiz and on the test. One time, I will ask you to write out the complete ionic equation. But if I had a multiple choice question and I ask you about the net ionic equation, do you really want to sit there and write all that out? Or would you like to do a shortcut? Did we do a shortcut yesterday? We'll do it again. Watch. See right here? Watch. Tell me in words what the 2 products are going to be. Ammonium nitrate? Is that going to be precipitate? No. You can look it up if you want. What's the other one? I'm going to look it up. Oh. So lead 2 chloride is going to be the solid, all right? So I write that down. I write it down. And then what's the only way you could have made that?
Lead 2 plus.
You had to have a lead 2 ion that was dissolved in water. And what else?
2 chloride.
2 chloride ions dissolved in water. See how fast that is? Let's try this one. What's the net ionic equation for this guy? What are the 2 products in words? Sodium nitrate. Is that going to be a precipitate?
No.
All sodium salts are soluble? All nitrates are soluble? Nope. What's the other one? All right, I'll look that up. All right, it's going to be a solid. What's the only way you could have made that?
Silver and
What? You have to have a silver ion, and what else? See, I'm done. That's pretty fast, isn't it? I will make you do the complete ionic equation because I want to make sure you have that skill, but I want to show you how shortcuts will tell you quickly what the net ionic equation is going to be. All right, are you ready? Did I give you one yesterday where I read it verbally and you had to come up? Did we do that yesterday? Was it the one with iron in it? Did everyone happen to have their notes? Okay. Did I ever go over the answers of that or not? Let's go over it one more time. I'm gonna magnify the screen, but when I'm not using the book, let me know if you still have trouble, if you're having trouble seeing it, all right? Excuse me. All right. Look at the notes. Were you able to write out the chemical equation, which the author calls a molecular equation? Were you able to balance it correctly? Were you able to predict whether or not the product was going to be a solid or whether it was going to be dissolved in water? Were you able to do that? Okay, that's great. That's great. Now, let's do the complete ionic equation. What's over here? What's this made of right there?
potassium.
3 what? 3 potassium ions and
3 hydroxide.
and you have to put the charge on there because they're ions, aren't they? And are they dissolved in water? Yeah, that's why I put AQ. What's over here in this beaker?
1 iron,
What kind of iron?
3
ion,
Which one?
ferric.
Right, very good. +3, isn't it? So I got a +3 ion, and what else? Please do not tomorrow write NO3 subscript 2. Don't do that. What's this compound made again of? 1 iron ion and what? 3 nitrates. You get that? That's what it is. Okay. Now you come over here and look at this part. How about the potassium nitrate? That's going to be what? It's aqueous. 3 what? 3 potassium ions and what else? That's it. That's pretty easy, wasn't it? What about this other guy? What do I do with this guy? Leave it alone. And so what's the net ionic equation? There it is. And if you want to do the shortcut, that's what you'll get. Do the shortcut, you'll get the same answer. All right. You want to do one more? All right, let's do one more. And if you can get this right, and I'm going to see how fast you can do it too, all right? I want you to speed up a little bit. I'm going to tell it to you in verbally in English, and you see whether or not you can get the regular chemical equation, the complete ionic equation, and the net ionic equation. You think you can do that in under 2 minutes? How about under 3, under 2? I want to mention to you that originally I thought the test next week would be on Tuesday. I did move that to Wednesday. I want to make sure we have at least one day, a good study day. So I'm going to move that to Wednesday, and there were no other tests that day as of right now. All right, here we go. Are you ready?
Yes.
Impress yourself, okay? Right now, impress yourself. As soon as I mention it, you get to town. You go to town. Did anybody ever tell you that? Go to town?
Yeah.
Okay.
Yeah.
All right, here we go. Aqueous solutions of sodium sulfide and copper 2 nitrate are mixed together. Aqueous solutions of sodium sulfide and copper 2 nitrate are mixed together. If a reaction takes place, write out the chemical equation, the complete ionic equation, and the net ionic equation. One more time. Aqueous solutions of sodium sulfide and copper 2 nitrate are mixed together. If a reaction takes place, write everything out you can write. And I'll start the clock on the 6th. All right, and we'll go. See if you can do all that in 2 minutes.
Can you say it?
Yep, one more time. Aqueous solutions of sodium sulfide and copper 2 nitrate. Because this is regular class, it's not a quiz, it's not a test, it's okay to make some mistakes, but you want to try it. And then when you find out what your mistake was, then you learn something. Well, I bet yesterday you probably thought to yourself, I can't do that complete ionic equation thing. Got a magnifier.
It was copper, right?
What?
It was copper, the second element.
Second element, what's that mean?
I mean, like the.
Yeah, it's thin as copper.
Copper 2 nitrate was the second reactant. Copper 2 nitrate. Okay, try to impress yourself or find out what your weakness is. One more minute. Now, if you can't do it in 2 minutes, that's okay. It's okay, but you got to figure out what slowed me down. Okay, what we're gonna do, I'm gonna pick somebody. Natalie, you feeling pretty strong today? Even if you don't, I'm gonna help you, okay? Anything that's not strong, we're gonna help you with, all right? I'm ready to go. Tell me what to write.
NA plus 1, and then S minus 2 aqueous, plus Cu plus 2, NO3 minus 1 aqueous, yields NA plus 1, NO3 minus 1 aqueous, plus Cu plus 2, S minus 2, solid.
What do you think? Feeling pretty good about that? I noticed over here, this was +1 and -1. That sounds like a compound to me. And this was +2 and -2. That sounds like a compound too. But something doesn't seem right here. You have +2 and -1. You thought that was a compound.
2 nitrates.
What now?
2 nitrates.
Don't we need 2 nitrates?
And then 2 sodiums.
Okay, see that? Everybody okay on that? Now, if you did happen to make that mistake, you can fix it, right? But what if you tried to balance the equation, you had the wrong formulas? And it's all messed up, isn't it? Does everybody have the right formulas? Okay, and I'll bet she looked that up and you found out it was a solid, right? So it is going to happen, isn't it? All right. As a matter of fact, I'm going to go ahead and do the net ionic equation right now. CuS. And what's the only way you could have possibly made that precipitate?
One copper iron.
Copper iron, all that.
Copper
Copper
ion.
2.
Copper 2 ion. And what? All right, I'm ready. Check your, did you have that as your net ionic equation? We're going to find out. Yeah, we're going to do the long version anyway. You did a good job on that, all right? What's your compounds, right? Watch how you write your compounds. All right, Bronwyn, you take over. I'm ready. Go.
2 sodium ion aqueous.
Wait a minute. Isn't it Na subscript 2? Hey, listen. Isn't it Na subscript 2?
There's 2.
No. No, there's no diatomic sodium.
Never.
All right, go ahead. Plus what?
Sulfur aqueous.
Sulfur minus 2 ions? Yeah, aqueous, okay.
Plus copper 2 aqueous. Plus 2 nitrate.
Very good.
Yields 2 sodium aqueous.
Oh, you know what? I corrected your formula, but guess what I didn't do? I didn't balance it. 2 sodiums. You know how I knew that? As soon as you started doing that, I knew that something's wrong because, see? So we didn't balance it, did we? Oh, is it balanced now? Oh, that's easy. Okay, go ahead.
Yields 2 sodium plus 2 nitrate aqueous plus copper sulfide.
All right, cross out. Wee. Oh, wee. Now, the only thing left should be that right there, isn't it? Is that right? How about you? Feel comfortable with this?
Yeah, better. Yeah.
Okay.
This part's not that bad.
All right. So what you're looking at here is, let me get my phone out here. What you're looking at is a double replacement reactions, but if you had to classify it, you'd say, yes, it's double replacement, but we can also say it's a what? A precipitation reaction because it was the formation of that solid precipitate is why it happened. Yes?
What if you have like the first half of the equation, and then like there's no stuff on the right side of the yield, like so how do you know if it's double replacement? It's
Okay. Good question. No. Excellent question. At this point, when you have AB plus CD, you're right. If you were a PhD chemist, you'd know some examples where it didn't happen. But if you have AB plus CD, it's going to be double replacement, or nothing's going to happen. So I agree with what you said. It would be the AB, you know what I'm talking about? AB plus CD. Great question, actually. All right. Now, what I'm going to do is there's a page, page 178, 179. There's another kind of double replacement reaction. And I'm going to give it to you right now, okay? So tell me whether or not this is going to happen or not. Ready? Nitric acid, solutions of nitric acid are mixed with solution of potassium hydroxide. Nitric acid solution is mixed with a solution of potassium hydroxide. And what do you think is going to happen there? Hydroxide. Okay, so what am I mixing with potassium hydroxide?
Nitric acid.
How's that? How do you write that? And of course, all acids and bases, by their definition, are solutions. And how did I know that the first one was an acid? Yes, I said it was nitric acid, but how do you know by looking at it?
Because there's the H.
Starts with H. Even acids are even named differently, aren't they? Because who's the star of the show? This guy.
H.
And when you put this thing in water, what's it going to break up into? Hydrogen ions, and that's what makes it an acid. And when you put this in water, what's going to happen?
It's gonna break up.
You're going to get this ion, and that is what makes it a base. So let's see what happens. Do you think this reaction is going to take place? Give me one of the products.
Let's see.
Hydrogen.
Hydroxy, H2O.
Oh my gosh.
What do you mean now?
Oh my gosh.
What's the other one?
Potassium nitrate.
And we already know that that's aqueous, isn't it? Is this going to happen or not?
Let's check.
Yes,
That's
it's
good.
driving factors,
Let's
like
driving
formation of a
factor.
liquid.
Yeah, formation
Not a
of water.
liquid.
Formation of water.
Right. One of the driving forces is the formation of a solid, but another driving force is the formation of a really stable compound called water. And so this one is also going to happen because now the driving force is a formation of water. And this is a famous reaction. Excuse me. It's called acid base neutralization. Now, for example, I bet somebody you know, it might be yourself, it might be your parents, your uncle, your grandparents, somebody, you've probably heard of somebody, when they ate certain kinds of food, they felt like they got heartburn, or they felt like, and what happens is, some people have it where you put, if they eat pizza, for example, they'll make too much acid. The stomach gets tricked into making so much acid that sometimes the acid even comes up all the way up close to their throat. And they call it heartburn, which has nothing to do with the heart, but it's a pain up here where your heart is. And it's really extra acid. So they go and they find maybe a bottle of Tums, or another called Mylanta. And if you'll look, wait a minute. If you'll look at the ingredients, number one, when you make an excess acid, you're making a solution that has a whole bunch of these floating around, and that's what's causing your pain. So Tums and Mylanta have, some of them have calcium hydroxide, magnesium hydroxide. You get it? So what is that? Why is that going to help?
Because it's a base.
Yeah, it's a base. And what's going to happen is the base is going to neutralize the acid. So let's go ahead and write out is this balanced already?
Yeah, no.
Yeah, no.
Yes, it is.
It is. All right, ready? Let's do the complete ionic equation and see if you can beat me. Ready? Go.
And you're the man.
Holy. He's the news of this.
I practice the same.
I'm sort of, there we go. Did you have something? Did you have something like that?
What's the last thing you wrote next to
All right. Wow, I'll do that every day if I can get a laugh like that. Okay, what I wrote was NO3 minus 1 aqueous. Okay, now, everybody okay?
So are we just,
Now, let's cross out the spectator ions, and what's interesting to me is that all the net ionic equations for all acid base neutralization, watch here, the ion that made you an acid is going to combine with the ion that made that thing a base, and it's going to turn into something that's not an acid or a base, it's neutral. It's not an acid or a base, it's neutral. It's neutralized liquid. Now, when I did a demonstration here about a week or so ago, one more than that, for example, I had some acid and some base, and I was going to pour them together, but they both look like water. So what I did, I put this little indicator in there, and the indicator, if it's an acid, it stays clear. So I put it in the acid, and it was clear, and it's called phenolphthalein. And then I add some base, and it turned purple for a minute, then back to clear. Now what that meant was, for a time, the OH hit the phenolphthalein, turned it pink, but then the OH got neutralized, and then there was, look at me, there were more of the hydrogen ions than there were hydroxide. And I put some more base in there, and put some more base in there, and then I got to the point where every one of the H's were neutralized by the OH's, okay? Everybody got that? And that's, when that thing changed, I knew that's when neutralization had taken place. And that means I could have even picked it up and drank it, and it would have been just water. The problem with phenolphthalein is sometimes it'll make your pee look different colors. So I'm not going to do that.
how do you know it does that? Like, whoa, Daniel.
All right, wait a minute.
Daniel.
Wait. Okay. All right, wait. I know what I'm recorded, but here's what I will tell you. I've never done that. I've only read about it. But I have, when I was a teenager, I did see somebody at a house. I did see, it happened to be a boy, and I did see a boy who knew he was having flatulence, and I didn't know, I think I'd ever see it in my whole life, but he actually pulled down his pants and lit a match, and I did see that thing catch on. I saw the fart catch on fire, and I tell you right now, I know that gas that's produced does catch on fire. I will tell you.
Wow. Wait, can you summarize that again?
You have to be careful about that. Okay. You have to be careful about that. Okay. All right. Yeah. But I didn't think I'd ever see that in my life. I've heard of it. I didn't think I'd ever see that in my life, but I did. All right. Well, now, what I'm going to do is, I'm going to move on a little bit here. I'm glad I'm moving on. I'm going to move on. I want to show you this last page here. And we're going to do a little bit of new stuff today. And then I'm going to review the new stuff. There's only a little bit of the new stuff that's on the quiz. But what I'm going to do is let me cover this up so you can't see everything. All right, well, here, let me start here. And by the way, I'd like you to read tonight pages 180 to 183. It's true that if you don't read it, but you like to pay attention, you'll be okay. But if you read it and then come to class, it might make more sense to you. Let's take a look. Here's what happened before this chapter. You knew there were how many types of chemical reactions, and this is for first-year chemistry students. You knew that there were this many. There were 5 of them, weren't there? Double replacement, single replacement, synthesis, decomposition, and combustion. So you knew that, right? Now, you'll read in this chapter, and I'm going to tell it to you, there's another way to classify reactions. Now, we're gonna classify them based on what the driving force was. So now we know there's double replacement, but there's two kinds. There are two kinds of double replacement. What's one of them? And the driving force was the formation of a solid. Next, another double replacement would have been what?
Acid-base neutralization.
And the driving force was,
Formation of water.
okay, now, everybody with me? Everybody say, we now know there are two kinds of double replacement reactions, and that's why they happen. But now, the last part of the chapter is big. It's a big idea. All right, we have plenty of time. We have plenty of time to learn it. It's a big idea. And the big idea is that single replacement, synthesis, decomposition, and combustion, they all have the same driving force.
Yep.
And what is it?
Transfer electrons.
It's the transfer of electrons. Now,
I don't know.
the transfer of electrons means somebody's going to lose electrons and somebody else is immediately going to gain them. Now, I want you to think about this. If you start losing negative electrons, you're going to turn into something positive, aren't you? But what if you gain negative electrons? You're going to turn into something negative. That never happens in double replacement. Every double replacement reaction you just did, nobody changed their charge at all, did they? That tells me that's not the driving force for double replacement. But what is the driving force? It's this thing here. Now, they made up some fancy words. One of them is called oxidation, and one of them is called reduction. And I'll tell you how to memorize those in just a minute. But imagine a chemist saying this. Well, what kind of reaction was it? Well, you know, those oxidation and reduction reactions. Oh, you mean the oxidation and reduction reaction? Yeah, the oxidation and reduction reactions. Do you like saying that over and over?
No.
And how about the biologist? Deoxyribonucleic acid. Well, what about the other deoxyribonucleic? Oh, they're real people. So what did they decide to call deoxyribonucleic acid?
Redox.
DNA.
Yeah.
And what did chemists decide to call oxidation and reduction? You know, I'm not saying they didn't have dates on Friday nights, but maybe somebody didn't, and they were sitting around and say, I want to say something besides oxidation reduction.
Yeah, I do that.
Oxy-redo, Anyway, the one that seemed, and I wasn't there, but the one they came up with, and I think they liked saying it, redox.
That's cool.
It stands for reduction,
Let's change the meaning of it.
oxidation. Now let me tell you what that means, okay? And when I went to college, I never heard that word in high school, but when I went to college, my biology professors were saying, what's a redox reaction? And then I went to chemistry, what's a redox reaction? What? I had no idea at all what they were talking about. But you will, and I'll show you how to memorize it. Okay. Now, ready? I even had a student one year, they did an extra credit project, and they found a picture of a lion, his mouth was wide open,
Oh.
and they wrote G-E-R coming out, like grr, okay? Not G-R-R-R, that's the way a cartoonist would do it. But anyway, Leo, the lion, says grr. Let me show you what that means. Ready? If you lose electrons in a chemical reaction, if you lose electrons, you got oxidized. Oxidation took place. And what's the GR stand for?
GR.
If you gain electrons, you got reduced, or reduction took place. I need everybody to be quiet, okay? I gotta get this. Now, what I'm gonna do is, I don't have a little bit of time here. About 2 minutes. I'll review this again tomorrow. I only have a tiny bit of this, but I want to show you something here. And I picked a synthesis reaction. I'm going to prove to you, I will prove to you that this thing is redox. And here we go. We have some rules, okay? Now, somebody made up some rules to play this game. And rule number 1, all right? We have to assign these oxidation states, and it's pretty simple. Number 1, if you're an element, then you're not combined with any other element, then your oxidation state is 0. Now, look up here. I know what you think I said. I never said this. I know you want to put Na+1. I have never said the sodium is +1. I have said 100 times sodium is +1 in a compound. What is sodium when it's not in a compound? It's not an ion. What is it? It's 0. It's not diatomic.
What are you?
Now, here's chlorine. Chlorine is not -1. Chlorine is -1 when it's combined with another element, a different element. But chlorine, that's just the element chlorine, is 0. Well, now, I'm going to put little zeros here because they're just plain elements, aren't they? But here, what is the charge or the oxidation state of sodium in a compound? It is +1. And what is chlorine?
-1.
All right, now look at me. How in the world did you go from having no charge to being +1? How did that happen?
You're losing
You
electrons.
had to lose a negative electron to become more positive. And what did chlorine? What happened to chlorine? You started at 0. How'd you get negative? I what? I gained some negative electrons. I gained a negative electron. And that happens instantaneously at the same time. And that's what redox is all about. And they're all 4 of these will fit the redox model. And I'm gonna do this again tomorrow and let you try some on your own. Like I said, the quiz is on the second half of the period. I don't have like maybe 1 or 2 little questions about redox, okay? All right, so anyway, if you have time tonight to read page 180 to 183, you can. And I think I'm done for the day, so I'm going to stop that.